Okay, we're back here, part 2 of Fundamental Theorem of Algebra. I have here another problem. This one's not as long as the previous one, but certainly if you can understand what I did on the previous one, then this one should be a bit easier. So I'm going to encourage you to pause the video and try this problem, try to factor it. A couple things to note before you do start that, though, is that it's a third powered polynomial. So we know what does that mean? That means that it has exactly 3 zeros. Now also, because it's third power, we know that if we were to graph this thing, it is going to behave generally the same way as the regular x cubed graph does. It's going to do something like this. So this is a good indication that we're probably only going to have one real zero, and the other two are probably going to be complex. So feel free to use the graph to get yourself started. Pause the video and resume it when you're ready to, and I will go ahead and start. First thing I did was I entered this equation into y equals. Let's see, I have that down here. The other two graphs have been turned off. This one's on. By the way, if you want to know how to do that, you just put the cursor on the equal sign and hit enter, and that activates that equation, or it deactivates it, just so you know. So I have the equation, I graph it. I'm just going to use a standard viewing window to start with, and actually understanding the shape of the graph, a lot of people might try to mess with this window hoping to find some kind of a parabola, but keep in mind what the overall shape is going to be like. We talked about left-hand and right-handed behavior a few sections ago, so keep that stuff in mind. So when I look at this, it looks like -1, -2. It looks like this is -3. So I'm going to start by dividing by -3. So we are going to put -3 inside of a box, meaning the factor, just to remind you again, a lot of people get confused on this. We would expect that the factor is x plus 3, right? But we're subtracting a -3, so that's what goes inside the box. Or some people think just use the opposite. So anyways, here we go with the factoring. I'm sorry, the division. So I'm going to start by dividing 1x cubed, make sure I have all of the coefficients represented. The x cubed, the x squared, the x, and the constant. Pause as you need and resume. Okay, we do the process. And we get our zero remainder, which we fully expected. So constant x squared. So what I have here, just to keep a running tab, this means that x plus 3 is a factor. Remember, the opposite of what this number is what goes inside the box. Okay? Or more formally defined, what number is being subtracted from x. This is the same as x minus -3. So anyways, now I'm left with the function here, which is x squared plus 16. Well, if that equals 0, if I'm going to figure out what makes this equal 0, I subtract the 16 over, and I know that I have to take plus or minus the square root of -16. There's a negative in there, I almost forgot. Well, this is going to be plus or minus 4i. So that's going to give me two factors, x minus 4i and x plus 4i. So the factored version of this guy, completely factored, is x plus 3 times x minus 4i times x plus 4i. Okay, hopefully that one went well. So on to a slightly different type of problem here. This time we're going to ask that you find the polynomial. It's like working backwards. Find the polynomial if we tell you what the zeros are. So you can imagine you can start by writing binomial factors and multiply them out, and we can end up with what the polynomial is. So basically, find the polynomial with zeros of 4 and 2 minus I. Now this might look a little bit weird at first, but I think after a couple of these you'll get the hang of it. So if 4 is a 0, that means that I have a factor of x minus 4. Okay, we're probably okay with that. Now here's where things get weird. If 2 minus I is a factor, just like here I took x minus 4, well, I'm going to take x minus 2 minus I. But I keep in mind that complex zeros occur in pairs. So if 2 minus I is a factor, well then 2 plus I is a factor. So I am going to have another guy over here called x minus 2 plus I. See how that looks to you? Now this could become ugly or it can become pretty neat depending on how we approach it. The way I'm going to highly encourage that you approach this is this way. We are going to rearrange some stuff here. If I distributed this minus through, this becomes minus 2 plus I. And then I'm going to move the parentheses. So I'm going to change this to say x minus 2, close the parentheses, and then what would that have been? That would have been a plus I. Do the same thing over here for a very good reason I'll show you in a moment. So I'm going to distribute and then regroup. So it's going to be x minus 2 minus I. The key to this is that I've got x minus 2, think of that as one thing, x minus 2 plus I, and over here I have x minus 2 minus I. Well, just like when I have x minus 3, for example, times x plus 3, hopefully we're getting familiar enough with this that that jumps in our mind right away as, oh, that's x squared minus 9. The difference of two squares, and it factors like that. That's what's going to make this an easier problem or a shorter problem to do. Because when we proceed from here, just keep on trying to make this look neater. And I imagine what this is going to look like when I multiply this out. Well, the first term, like here I had x squared. Well, now I'm going to have x minus 2 squared. So I will put that inside of a parentheses here, I guess. Okay. The outer and inner terms, just like over here, 3x minus 3x cancels. I don't have any terms like that. Well, the same thing is going to happen when I multiply the outer terms and the inner terms. Those are going to cancel. And all I'm going to have then, just like here I had negative 3 times plus 3 to get negative 9, here I've got positive I times negative I, which is going to give me negative I squared. Now that just saved us a bunch of really ugly looking algebra that was going to make this a mess of a problem here. So we'll continue to multiply and shorten this thing up, and we'll end up with our polynomial. So I'm going to leave x minus 4 alone for right now. And let's take x minus 2 and let's square it. Well, that's going to be x squared minus 4x plus 4. And now this goes away because remember I squared is negative 1. So negative negative 1 is plus 1. So what I've got here is, x minus 4 times x squared minus 4x plus 5. So I've got one more duty here, one more job to do, and that is to multiply this stuff out. So we're going to do that by distributing. First I'm going to start with the x, and I'm going to distribute that to all three of these things. That's going to look like this: x cubed minus 4x squared plus 5x. Now I'm going to do the same thing with the negative 4. I'm going to send it through to all three things. Careful with the negative. Make sure you bring that with. So minus 4x squared plus 16x, and then I have minus 20. We combine our like terms, we have our answer. So our final version here is x cubed. Now I look, I've got a minus 4x squared and a minus 4x squared. That makes a minus 8x squared. I've got a plus 5x and a plus 16x. That makes plus 21x. And I got minus 20. So what I have here is the polynomial that has the zeros that we originally told you. That's probably going to take you a couple times of doing to completely grasp. Normally where people are going to go wrong with this is up here. Common mistakes to watch out for is that people might accidentally make this a minus and this a plus. It's going to be much easier if you just keep in mind that if 2 minus I is a root, 0, then 2 plus I is a 0, and that's what we're going to be subtracting. Just like here I said 4 is a 0, that means I have x minus 4 as a factor. So we'll give this a shot. This may take a couple times of doing to totally get. I'll give you some problems like this that give you the factors, or the zeros rather, and you are going to come up with the polynomial. So a quick recap: fundamental theorem says nth degree polynomial is going to have exactly n zeros. However, they may be, some of them may be complex. We take advantage of the shape of the graph. If you have to, use the rational zero theorem to help you try and figure out what numbers you might be dividing by. But this is probably going to be largely unnecessary if you use your calculator to help you get started. And that'll work as long as you get integer zeros. If they're not integer zeros, then your calculator might not be as useful, and this might become more useful. But we haven't seen any problems like that yet. Keep in mind that if you have a complex zero, it's going to have a conjugate pair that goes with it. And always make sure that when you're done finding the zeros, that you have as many zeros as you're supposed to, which is the highest exponent, a combination of real and imaginary zeros. Okay, here we had another problem, a little bit easier, same idea though. Once we find one factor, we're using synthetic division, and we keep on working our way down. And then lastly, we had the problem where I give you the zeros and you find the polynomial. So we'll try some practice problems here on this. So what we'll try for homework, for an assignment here, on page 140, we are going to do some multiples of 3. Be careful to do the correct problems. I'm trying to give you guys a good mix of problems, but not too many. So 9 through 24 multiples of 3. Okay, in addition to that, we will do number 25. I like that problem. It's a little bit more nasty than the other one, so probably one we'll end up doing in class together. And then finally 35 through 38. We'll work on these. We'll start, talking about these concepts tomorrow in class a little bit more. Hopefully you've had a chance to watch both these videos by then. And we'll work on this over the weekend, and hopefully we can kind of wrap things up a little bit on Monday. Enjoy.